Welcome. So in this video we are going to look at the basic differentiation rules that we have and see how we can write down their chain rule versions. Doing so, it will be a lot easier to differentiate any type of function that is a composite of basic functions. So recall that the chain rule says that if I have a composite function c of x, which is f of g of x, then c prime of x is f prime of g of x times g prime of x. Now there is another way of just rewriting that chain rule, which personally I prefer, and you get this version by replacing g of x by u. So then f prime of g of x becomes f prime of u instead, and g prime of x is just du dx, or you could just write u prime. So if we do that, we get that c of x is just f of u, so c prime x is the derivative of f of u, so that's what we have here in the equation on the left hand side, and f prime of g of x becomes f prime of u because we've replaced g of x by u, and g prime x is just the derivative of u, so du dx, or we could write u prime. So I prefer the chain rule written in that way, and I'll show you that I prefer it because it allows us to write any basic differentiation rule quite easily in its chain rule version. So for instance, take the basic differentiation rule that says that the derivative of sine of x is cos of x. Notice that this basic differentiation rule is just in the form the derivative of some function f of x, let's say, and on the right hand side I've got the derivative f prime x. Once again, the chain rule says that the derivative of f of u will be f prime of u times du dx. So to take this basic differentiation rule and adapt it to the chain rule, all I need to do is replace x by u, and in the end I multiply by du dx. So for instance, if I take this specific basic differentiation rule, okay, to get its chain rule version, all I need to do is replace x by u and multiply here by du dx, and I get this. So this rule here is what we call the chain rule version of the basic differentiation rule, derivative of sine x equals cos of x. So instead of having x now here, we have got u, which is a function of x. And again, the only difference is that on the other side, I not only have cos of u as the derivative, but I'll also have another factor, which is the derivative of the function u. Okay, so let's see how we can use this to compute a derivative. You will see that it's a lot easier than trying to decompose this function into a function, a composite of function f and g, and identify what f is and what g is, take the derivative separately and putting everything back together. So you'll see here that using my new chain rule version of a basic differentiation rule, I can do the derivative quite straightforwardly. So let's just think of this function here as sine of something. That something is a function of x, okay, as you can see, and I will call that u. Okay, so what I have here is that the derivative of sine of x squared minus 2 is just the derivative of sine of some function, u. Okay, now the derivative of sine of u, and this is where I use my basic, chain rule version of a basic differentiation rule, is cos of u, but times du dx. So let's not forget that part. It's very important. If I don't put this here, I will get the wrong derivative. So now I just replace u by what it is. It's x cubed minus 2, and du dx by what it is, which is the derivative of that function here, x cubed minus 2. So that's 3x squared minus 0, and I'm done. The only thing I will do is put that 3x squared in front of the cosine to avoid any confusion, and that's it, and then we're done. So it's a lot faster if we use conceptually that new chain rule written in terms of the u variable. It allows us to write all our steps quite easily. And this this slide here shows you on the right-hand side, on the left-hand side, a list of basic differentiation rule, and on the right-hand side, their chain rule versions. And as you can see, it's not hard to do. All I need to do is replace x by u and multiply by du dx the expressions that I obtained. So let's look at another example. So this is an example you've seen in the previous video. And here we're differentiating the cosine of the square root of x squared plus 1. So here there's a composition of three functions. There's the cosine function, the square root function, and then the polynomial function x squared plus 1. And I will differentiate this quite easily using my basic differentiation rule. So the first step is to see that I'm differentiating cosine of some function of x. So let's think of this as our u for now. So we've got the derivative of cos of u, so that's minus sine of u times du dx, and then I can replace u by what it is. It's the square root of x squared plus 1, and here I'll do things slowly. I'll just replace here u once again by square root of x squared plus 1, and since I haven't differentiated it yet, I will just put d dx in front of it to remind myself that I still need to differentiate the square root of x squared plus 1. This part, we're done with it. We're gonna maybe simplify things in the end, but at the moment, this part has been differentiated. Okay, there's no derivative for that anymore. Just that we just need to focus on that part. Now, if we focus on that part, okay, we're gonna apply the chain rule again because we see that this is the square root function composed with the polynomial function x squared plus 1. So let's think of x squared plus 1 now as our as another u, as another function of x. Okay, so I'm gonna apply the chain rule to differentiate this. It might be easier to think of the square root as a power function. So the square root of u is just u to the 1/2. If I differentiate this, okay, I need to apply a basic differentiation rule. It's the differentiation rule we would use when the function is of the type u to the n, and if I differentiate u to the n, I get n times u to the n minus 1. So 1/2 minus 1 gives me a power of -1/2. And let's not forget the times du dx. Okay. So once again, all I need to do now is replace u by what it was. It was x squared plus 1, and here I'm still left with one little derivative to do, which is my du dx, and now it's the derivative of x squared plus 1. If I differentiate this I get 2x, and I'm done differentiating now. What I can do is try to simplify and rewrite everything nicely. So you can see that there's a factor of 2 here that cancels, and otherwise I could leave the exponent as -1/2 here. Personally, I prefer to have positive exponents when I write down functions, so I'm going to shift this to the denominator, and also put a square root instead of a power to the 1/2. And so we're done. So we just found that the derivative of cosine of square root of x squared plus 1 is minus x sine of the square root of x squared plus 1, all of it divided by x squared plus 1, which is the expression we had obtained in a previous video. So now I'm going to look again at another example that we had done before, which is the derivative of x squared times e to the 5x. Now, first of all, this is a product of two functions. So the first thing we need to do is a product rule. Okay, so I'm differentiating x squared times the second function e to the 5x plus the first function x squared times the derivative of the second. So the derivative of x squared is straightforward. Okay, it's going to be 2x. For this part, it's the derivative of e to the 5x, not just e to the x, but e to the 5x. So it's again a composition of functions. It's the exponential function composed with the function 5x. So I have to think of this as e to the u. Okay, and this is where I'm going to need the chain rule. So the derivative of e to the u, where you use a function of x, well, Okay, I know that the derivative of e to the x is e to the x, so the derivative of e to the u will be e to the u times du dx. Okay, again, let's not forget about that part. Afterwards, I can replace u by 5x, and I need to compute here the derivative of 5x. And that's quite easy. The derivative of 5x, well, this is a straight line with a constant slope of 5, so its derivative is obviously 5. And now I'm done differentiating, and what I can try to do is try to factor everything. So as you can see, I have a common factor of x, a common factor of e to the 5x. If I put everything together, I get this. So this is my derivative. And this is the derivative we had obtained also in a previous video. So the advantage of using a factored form for the derivative, okay, is that we can solve a problem like this one. Find where the graph of this function has horizontal tangent lines. Horizontal tangent lines are interesting because those are places where you're likely to find maximums and minimums, and we will use those in an upcoming section. So we will maximize functions, we'll minimize functions. All we need to know where the tangent line is horizontal. When the derivative is factored, it's quite easy to answer that type of question, because to find where the derivative is 0, I need to find where this expression equals 0. Right? I need to solve f prime of x equals 0. Now, if it's factored, a factored expression can only be 0 if one of its factor is 0. So either x is 0, either e to the 5x is 0, or either this bracket is equal to 0. So I have 3 possibilities. And for each of them, I need to solve the equation for x. So when is x equals 0? Well, that's trivial. That's when x is 0. When is the exponential function e to the 5x equals 0? Think about the graph of e to the 5x. Does it ever cross the x-axis? That would be where it could potentially be equal to 0. And if you think about it, it's actually never going to cross the x-axis. So this has no solution. So there are no values of x that satisfy this. As for this one, okay, well, this is pretty easy to solve. You send the 2 on the other side, divide by 5. So you get 2 solutions. You get that it's going to be 0 when x is 0, or when x is minus 2/5. So those are the 2 points, 2 values of x where the derivative of f is equal to 0, or where the tangent line is horizontal.